Hey everyone, welcome back. Professor Sebastian. We're in our statistics class notes on the bottom of page 55. We have not started example 68 yet. We're actually working to understand the regression line equation when doing regression analysis. So in example 68, we want to use the same table with the heights and weights for 6 people that we just did in example 67. Okay, came up with this regression line equation when we used height as the x variable, which is often known as the independent variable, could be called the predictor variable, or it could be called the explanatory variable, and weight is the y variable, which is the dependent variable, the predicted variable, the response variable, or the dependent, or the, yeah, that's it. I already said that. Okay, so here's the table again. But now I'm going to switch them up. I'm going to let weight try to predict height. In other words, I'm going to let weight be the x variable or the independent variable and height be the y variable. And you see that the regression line equation is significantly different. So if we go back to StatCrunch, and I'm going to change these up. I'm going to edit this, and I'm going to switch the x and the y. So x is now weight, and now variable is height. And we'll recompute it. And you can see this is what we get. 52 point, I'm sorry, right here. Height, so this is y equals b plus mx, where we let y be the height now, the dependent variable, etc. And I cut and pasted this into your notes. Okay, so going back to the notes, here's where that is again. Notice the correlation coefficient stays exactly the same when you switch x and y, but it significantly changes the regression equation, of course, because we've changed y and x. If you remember back from from algebra, this is simply the inverse equation, but we don't have to worry about it. We're just letting StatCrunch do all this. Okay, so the correlation coefficient stays the same. The new regression equation is height equals 52.397 plus 0.086 weight. We have a new y-intercept, and we have a new slope, of course, because the x and the y are switched. Okay, now we want to be able to actually interpret the slope and the y-intercept to make sure we have a deeper understanding of what the regression line brings us. And I want you guys to be able to do this. So how do we interpret the slope of the regression equation? The slope tells us how much that the y variable changes when the x variable is increased by 1 unit. Okay? A slope close to 0 means that there's no linear relationship between x and y. So interpreting the slope. So here we have a slope of what? So this is in the form of y equals b plus mx. So the slope is 9.029. The y variable is weight, right? Y equals b plus mx, and the x variable is height. So the interpretation here is that if the x variable is increased by 1 unit, then the y variable, the predicted y variable, increases by the amount of the slope. So in that case, if the height is increased by 1 inch, because our units were inches for height, the predicted weight, right, increases by the amount of the slope, which is 9.029, and since it's weight, that's pounds. All right, so let's do another example. In the previous example, I didn't change the number. I'm sorry about that. The association between car's mileage and its sales price was modeled with a regression line. The regression equation was given this way. Okay, so this should have been a comma, by the way. Price equals 15,867 minus 0.034 miles. So what does that minus 0.034, right, mean? That's the slope. M is minus 0.034 because it's b plus mx. So the negative sign goes with the slope. What it means is that for every additional mile, 1 mile, that a car is driven, its predicted price will decrease by $0.034, or 3 cents and 4 tenths of a cent, right? 3.4 cents, or $0.034.